Okay, let's pick up where we left off last time. We have a little bit more review to do, and then there's just so much material that we need from other areas to even start talking about digital communication. So let me first define something that you probably already know: power and energy of the signal. Let's say x of t is a signal. It's a realization of a random process. Then the energy of a signal x is defined as integral when t goes from minus infinity to plus infinity x of t squared dt. In other words, the area under the curve of the magnitude square of the signal. And then the power, Px, is defined as the limit t goes to infinity, 1 over t, integral t goes from minus infinity to plus infinity, x of t squared dt. I just noticed in the notes, 1 over t factor is missing, so for those following the notes, make sure you put it in there. So these are the standard definition of the power and the energy of a given signal. Let's define another important quantity, which is autocorrelation. Autocorrelation function of a random process. Let's x of t be a random process. Then autocorrelation function of this random process, we're going to designate it as Rx x of tau. Is going to be expected value of x of t times x of t minus tau. It is customary to put the complex conjugate here if this is a complex process, but I'm going to put it here and kind of ignore it for the rest of the class because we're going to be dealing mostly with real signals. So this is the definition of the autocorrelation function. Now, notice here, this is defined through ensemble averaging, right? I'm looking at the various realizations and I'm taking expected value across all possible realizations of this random process. If the process is ergodic, if x of t is ergodic, then we can actually substitute this ensemble averaging here using the time domain averaging. And what that allows us to do is to estimate what the autocorrelation function looks like just by using one realization of that particular process. In that case, Rx x of tau can be estimated as limit when t goes to infinity, 1 over t, integral over t, x of t times x complex conjugate of t minus tau d. Right? So it's easy to understand what is it that you're doing. You're taking your signal x of t and you are multiplying it with a delayed version of itself, and then you're integrating this over time, averaging 1 over t dt. And then what you end up here is Rx x tau. Now, what is the reason why we care about autocorrelation? Why is this important to us? Let's go back, think about what is it that we talked about last time. We defined the notion of stationarity, right? But we treated only amplitude domain. We said that the signal is stationary in amplitude domain. It's if the PDF of the amplitudes does not change over time, right? And then we said in a wide sense, you know, we don't have to preserve the entire PDF, only the first two moments can stay the same, the average value of the power, and this is a wide sense stationary. But in a strict sense, if the process is stationary in the amplitude domain, the distribution of the amplitude does not change over time. Now, I can define two processes that have, let me actually do that. Consider these two processes. They're gonna both be distributed the same way in the amplitude domain. Which means, let's say they kept there in between this particular range. And let's say the first process kind of looks like this. And then the second process looks like this. Right? If I look at the distribution in amplitude domain of both of these processes, let's say it looks somewhat like this. Right? So it's the same. But what can you tell me about these two? Are they the same processes? They're distinct. How are they different? How do these two, which domain are there different in? In a time domain, right? So you can have two processes which have the same behavior in the amplitude domain. Let's say they're normal in the amplitude domain, normally distributed in the amplitude domain, but have a different behavior in a time domain. This process is much faster, right? Changes faster. So that's the second domain that we need to characterize. And we said when we talk about processes, there are two domains we need to talk about, amplitude domain and the time domain. We can talk about this other domain either as a time domain or a frequency domain. And it turns out that we can describe the process in this domain, in a time domain, using the very simple autocorrelation function. Because if you look at how we can determine autocorrelation function, it's relatively simple to do, right? I take the same, if the process is ergodic, then I can take a single realization of this process and then delay it by different amounts of tau, and then just determine what autocorrelation function looks like. Let's say this is tau. If I don't delay it, I end up with the power. And then if I delay it a little bit, I end up with the value, you know, and then I can actually generate the autocorrelation function. And what, so I'm kind of going ahead of myself and I'm telling you why we need autocorrelation function. We need autocorrelation function because this will be the way for us to specify the behavior of the process in the time domain, right? You know, so then we have two descriptors of every random process. We'll talk about the PDF of the amplitudes and the autocorrelation function in the time domain. So that's where we're going. But before we reach there, we define the autocorrelation function. So let me look at some of the properties of the autocorrelation function.
Excuse me, Professor.
Go ahead.
If x of t is not ergodic, so
then you have to go back to this definition. Right? That means you actually have to line up as many realizations as you can, calculate the product for each realization, and then average across all possible realizations.
also you standardize all.
So we have to, if the process is not ergodic, then you cannot substitute the time domain averaging for ensemble domain averaging. The autocorrelation function is defined strictly in ensemble through ensemble averaging. But if the process is ergodic, then you have to do it using the time domain. And for this course, you know, the distinction is only important at this point because most of the processes that we're going to be dealing with, like speech signal and noise being the most important one, happen to be ergodic. So we kind of like out there. And we'll use the time domain averaging, but at least somewhere in the back of your brain, remember the proper definition for it, because I can guarantee, you know, if you end up working on this, it will catch you where you least expect it, right?
Yeah, Professor, could you give us a physical understanding of the autocorrelation function?
Yeah, that's what I'm going to spend most of today, right? So, because it's a very important concept. It's one of those concepts that you know, it's remarkably simple and remarkably insightful, right? It's one of those, let me just define it and then we'll spend playing with it and you will see how it tells you a lot. And my emphasis here is actually going to be on the physics of things. What does it mean? But some basic properties of autocorrelation function. First property, R of tau is even, which means R of minus tau is the same as R of tau. That is immediately apparent from this because you can actually, let me just do this. Let me just actually show that this is the case. So if you look at R of tau, this is a limit when t goes to infinity, integral when t goes to minus infinity, plus infinity, 1 over capital T, x of t, x of t minus tau, d tau. Now I'm dropping the complex conjugate because we're dealing with real signals. And then R of minus tau ends up being limit when t goes to infinity, 1 over t, integral when t goes from minus infinity to plus infinity, x of t times x of t plus tau d tau. And introduce now, not d tau, dt in both of these cases. Now introduce the, so here I'm delaying the signal before multiplication, and here I'm advancing the signal before the multiplication. But let's introduce the substitution here, where mu is equal to t plus tau. Then t is going to be equal to mu minus tau. And dt is going to be the same as d mu. Right? If this is my substitution, then from here, t is equal to mu minus tau. Right? Just take the tau on the other side. And dt is the same as d mu. So I can transfer this integral into limit when t goes to infinity, 1 over t, integral. Now, when t is in minus infinity, where is mu? Minus infinity. So mu goes from minus infinity to plus infinity. X of, instead of t, this is mu minus t. And then x of mu, d mu. And now look at this integral and this integral. They're the same. Right? So autocorrelation function is an even function of tau.
I have a question before we go too far. Actually, this is kind of like fundamental. So what is the purpose if we do autocorrelation in our like random process? What is the goal that we need to
Yeah, that's the same question he asked. Give me 5 minutes. I'll get there.
Okay.
Right? We'll get there. So right now we define it. I want to get some properties, and then we're going to go through example and discuss what this means to us. Why do we care? Well, I kind of hinted at it over here. Just to give you a sneak preview here, we're going to use autocorrelation function to capture this difference. See, if I look at these two processes in a magnitude amplitude domain, they look the same. They go through the same magnitude values with the same probabilities, but they're not the same process. What's different between them? And that's what we're going to capture with autocorrelation function. Okay, so that's the first property, and the second property that I want to also highlight is that the maximum value of autocorrelation function occurs for delay of tau equals 0. So, second property, R of tau is maximum when tau equals to 0. In that case, r of 0 is equal to limit when t goes to infinity, 1 over t, integral when t goes from minus infinity to plus infinity, x of t times x of t. Now, how do we call this? Power, right? So one of my, favorite questions for those comprehensive exams, master comprehensive exams, I give a really complicated formula for autocorrelation function, and I ask, what is the power of the signal? Right? And a lot of times I get correct answer. You just substitute 0 and it's one value, right? There's hardly anything to do. But sometimes I get pages of kind of entertaining material, right? Right, so remember, the value of the power of the signal is the same as autocorrelation function for a 0 lag, and that's the maximum value of the autocorrelation function. Let's look at a couple of other important results. So, random process and linear system and linear systems. That's what we need to. This is the central thing that we need to understand. This is what our course is all about. We're going to having random processes traveling through some linear systems. So in most cases, this is the scenario we have. We have x of t, where x of t is a random process, and there is some filter that has an impulse response h of t, and there is output y of t. Now here's how we describe this system. If x of t is a random process, y of t is a random process too. Now, for any given realization of x of t, I can always determine y of t, right? So we know that from linear system theory. So for any given x of t, y of t is equal to what? X of t convolved with h of t. And you know how you calculate it. This is integral when x of tau, h of t minus tau, d tau, tau goes from minus infinity to plus infinity. So that's a useful result for us, but it's not extremely useful, right? Because remember, we are not designing our systems for known signals, right? This says if you know what x of t is, then you can calculate y of t, and that's important on its own. But we design our systems to handle random processes. So the best this is the best use the only use this is if I know, for example, this particular speed signal, then I can predict what happens at the output. But my goal is not to make a system that handles this particular speech signal. I need to handle speech, right? So we need a better descriptor. We need to understand what the linear system does to this process as a whole, right? It will map a random process at the input into a random process at the output. So we need the descriptors as a whole, right? So this is useful, but it's not going to help us a lot. The second result that we know is this. If x of t is stationary / ergodic, then y of t has the same properties. Right? And that's a big help, right? Because it tells us something about linear systems. They cannot change the statistical behavior, the fundamental statistical behavior of of the process. If the process is stationary and the system is linear, the output of the system is stationary as well. And the same as for ergodic. But the third one is the most important one. And this is autocorrelation function of output, which is RYY of tau, is going to be RXX of tau convolved with h of tau convolved with h of minus tau. Okay, so what is the significance of this? Well, autocorrelation function, the way we define it, is characteristic of a process as a whole. It tells us something about speech signal, all of speech, not this particular realization, but process as a whole. So what this equation tells us is how you get characteristic of the output signal by knowing your linear system and the characteristic of the input, not signal, process. How do you get the characteristic of the output process? By knowing characteristic of the input process and the linear system itself. So this is a mapping between two characterization of the process as a whole. Right? Go ahead.
Could you give like an example of mapping?
What do you mean example mapping? I can give you particular impulse
Because
responses.
you said
And
about the speech, but in speech, the signal is usually slightly changed whenever you have
correct. And how do you characterize this change?
by model.
And what is the
Yeah,
model?
that's-
This is one of these models. So this tells me how the autocorrelation function of the output will change as a result of the process propagating through this particular linear system. Now, this equation itself is a little tricky, and you know, it's easy. First of all, it's relatively easy to derive, right? You can actually try. You can say, okay,
Yeah, that's a to convolution and then.
no, but it's. Let me sketch the derivation. I mean, it is just the interpretation is not easy in the time domain, but we'll get to it, and then when we get to the end of this, you're gonna say, aha, this is our good old friend. So let me just sketch how you would. This one is easy to prove, right? You would say, okay, well, what is my RYY of tau? Well, this is the limit when t goes to infinity, 1 over t integral over t, y of t minus tau dt, right? So that's our y of tau. And then this is now, you would replace this as x of t convolved with h of t, and this is x of t convolved, x of t minus tau convolved with h of t minus tau. So you're going to have triple integral here. And then you're going to just change the order of integration and get this. So let me just take one more step. So RYY of tau is the limit when t goes to infinity, 1 over t, integral when t goes from minus infinity to plus infinity. And instead of y of t, you're going to say integral when mu goes from minus infinity to plus infinity, h of t, x of t, h of x of mu, h of t minus mu d mu, right? So that's your first integral. And the second one becomes integral when tau goes from minus, no, not tau is a good one. Another good. So nu goes from minus infinity to plus infinity, x of nu minus tau times h of so y of t is now t minus tau. So this x of x of nu times h
mu
of
minus t.
t minus tau minus
Oh, minus,
d,
yeah.
right? And then everything dt. Okay, so it's a little messy, but it's relatively straightforward. And then what you need to do is now jumble everything out around, right? Integrate, take everything with respect to nu, in respect to nu, whole bunch of things will cancel and you'll end up with this. But I don't want to go this because it's going to take 3 boards and essentially just prove this. You just have to take it at the face value. Now, what is the interpretation? It's not easy to see what the interpretation of this is, but it's a straightforward mathematics. It tells me, you know, if you know your autocorrelation function of the input and you know the linear system, I can tell you what the autocorrelation function of the output is. Okay. Now, to give some significance of this, we have to define one more thing, and this is the power spectral density of the random process.
Can we know the autocorrelation of the input without knowing the input?
Without knowing, okay. We have to be careful what do we mean by know, right? Knowing input would mean knowing this particular input, right? And if you know particular input, no need for any of this.
Right.
You know, I can deal it with this, right? So if you say something like, here's your input, what is the output going to be? It's easy, right? You just execute this convolution and you're done. But can you know the autocorrelation function of the input without knowing the input? That's actually what you're after, right?
Right.
What we want to do is, here's the legwork that happens before any of the communication stuff happens. You say, I want to design a system that handles, let's say, speech. So somebody says, okay, how do you do that? Well, you know, then you go back and you say, okay, what is speech? Speech is a random process. So what is it that I need to know? I need to know its behavior in a time domain and its behavior in a frequency domain, or time, the amplitude domain and behavior in a frequency domain. And then what is the behavior of speech in a amplitude domain? Well, how do I do that? Well, I take a whole bunch of speech signals and I look at their value in the amplitude domain. I generate a histogram and I plot that histogram. And when you do that for speech signal, it turns out that it has what is called Laplacian distribution. It looks somewhat like this, long-term speech, where this is the magnitude and this is a PDF. Let's say X.
But whenever it comes with speech, it depends on your time. And then
Okay,
respect-
wait. So this is behavior in a magnitude domain. What does this mean? If you look at speech as, you know, you've all seen speech signals, how they look like. Right? They're heavy around 0. There's a lot of samples that are small, right? And then very, very, very few samples are with high excursions, right? So it's kind of like mostly around 0. So that's in the amplitude domain. Now, so I've done that. So first task I did. Then a second task that you ask, well, what is the behavior of the speech along these different axes, along the time axis? And how I do that, I again take a lot of speech signals. I do out of tau for a lot of these speech signals, and in other words, I play them through, let's say, hardware that delays and then integrates, and I obtain the long-term autocorrelation or short-term autocorrelation of the speech signal. And now I have two descriptors. I have a PDF and I have autocorrelation function. And that comes with the speech signal without knowing particular signal, right? So this is how, when I say, how do I describe speech signal? Here's the Laplacian PDF, and here's the power spectral density or autocorrelation function. And we obtain that for every signal that we need to handle. And then what this does now for us, it tells us, okay, if you went through this legwork and you determined the autocorrelation function of the speech signal, I can predict how does the autocorrelation function change as it propagates through this linear system. Now, since we're doing a communication system, what is our goal? Our goal is to make sure that it doesn't change, right? So we need to make sure that when this h of t convolves this with this guy, that what comes at the output, this one is very close to this one. You know, that's the goal of the communication system when it comes to speech signal. But let's say I'm processing noise, I'm processing all the other things, then I'll be able to predict what happens, you know, when I present this signal to the linear. Now, it's going to be clear, you know, it's a little bit tricky in autocorrelation, because autocorrelation function is easy to calculate, but there is a dual of autocorrelation function that we like much better than autocorrelation function that I'm just going to introduce in a second. So to answer your question, it is possible, and that's how commonly we treat. You know, when we say random process, then the questions are, what's the behavior in amplitude domain? And you produce some sort of PDF. And then, what's the behavior in a time domain? Well, you can produce autocorrelation function as to characterize the process in a time domain. All right, but let me define one more thing, and I promise this is the last one, you know, for today. So this is the power spectral density of random process. And I'm going to define this by what is called construction. I'm going to actually define it by a set of steps that will tell you how you might create one of these power spectral densities. So let this x of t denote random process. A random process. This is our speech signal. And let x of t omega I be one particular realization. One realization of x of t. So again, what are these? This is a speech signal. This is 6 o'clock news. Right? So one particular realization of this speech signal. To define power spectral density, we're going to define a truncated version of this guy. So a truncated version of x of t omega I is going to be defined as xt of t omega I as this. It's going to be the same as this for t smaller than t over 2 and 0 otherwise. So what is it that we're talking about here? Let's say this is your t, and this is this particular realization, x of t omega I, and let's say this process looks somewhat like this. And let me do it this way because of my definition here. So put 0 here. So this is my particular realization of this process. So I'm defining a truncated version of this process in the following manner. I identify the duration of t. So this is t over 2 minus t over 2, and the length of this is t. Within this interval, this process looks like the one upstairs, and then it dies. So this is truncated version. You follow what I did? So just took my scissors and cut capital T worth of a signal, right? Now, why did I do that? Because now this truncated version is an energy signal, and it has a Fourier transform, right? So I can take the Fourier transform. I can actually determine what are the sinusoidals building this particular one. This may not be energy signal, because the area under the curve may be infinite and it may not have a Fourier transform. But this one does. So here's the process. So imagine now I have many realization of this process. Infinitely many. So this is my x truncated t omega 1. This is x truncated t omega 2. X truncated to t omega n, and so on, right? And I have an interval that's length of t, and before that it's 0, and then it kind of wiggles around and stops here at t. And then this guy does similar thing. And then this guy does, again, similar thing. All of them stop at this t. Okay? So, I can now take each one of these guys and I can determine the Fourier transform associated with this particular waveform. So this is going to be x t of now f omega I divided by t, and I take the magnitude squared, right? So not omega I, omega 1. And let's say the Fourier transform associated with truncated version looks somewhat like this for the first guy. So that's a Fourier transform. What does the Fourier transform tell me? What sinusoidals participate in building this particular realization of this random process? So if I want to build this one, I need these sinusoidals. Now I do the same for the second one, and it looks somewhat similar, but a little bit different, right? So this is xt of f omega 2 magnitude squared divided by t. And then I take all of them, and let's say this is, again, xt f omega n magnitude squared by t. So now I have the time domain, then I have the frequency domain representation of these signals. And then the last step is I now focus on a single frequency, let's say, or frequency band, let's say this band. And I look what happens. This is what is required, how much of this band is required to build this one, this one, this one, and so on. And then I do an average across the n-sum. So in a last stage, I say, okay, across all of these particular realization, I'm going to need this much of this band. And then this much of this band. And this much of this, kind of go across different frequency ranges. And you get one thing here that I'm going to call Sx of f. So what is Sx of f? It is going to be limit when t goes to 0, expected value of xt of f omega divided by t magnitude squared. Or I don't need to do omega because I'm averaging across all omega. So x of f magnitude squared. All right, so let me first try to explain this physically, and again, by going through this. So I have a random process. Let's say this is my speech signal. I have identified, because I have to work with finite, but in a mind experiment, there can be infinitely many possible realizations. And for every one of the realizations that I have in the time domain, I have obtained a frequency, a Fourier transform of it. Fourier transform tells me what sinusoidals build this particular realization, right? This is what I needed to have in terms of sinusoidals to build the 6 o'clock news. This is what I needed to have to build tonight's lecture, right? This is what I needed to have to build, inauguration speech or whatever, right? So these are the time domain, and these are the corresponding frequency domain waveform. Now everyone, just like this is every one particular realization in time domain, this is corresponding realization in a frequency domain, right? So this is, all of these are kind of random processes on their own. But I can now say, okay, on average, if I look at this frequency band, to build speech signal, I need this much of these frequencies, right? So if I average across all of these different Fourier transforms, I'm going to get one waveform in the frequency domain that I'm going to call power spectral density. Now, what do you think about this? It's complete nightmare, right? You never do this, right? But this is the mind experiment. What is the goal of this? If I talk about speech signal, what is the frequency domain make of that signal? What portion of the frequency axis do I need to build the speech signal on average, right? All of the speech signals. And what I care about is what is the range of frequency and what is the relative contribution to this particular random process. And I get that information from here, right? It takes me a while to get there, but I can, once I complete, I can say something like this. This is the range of frequencies that I need. As a matter of fact, if you look at single-sided, this is the range of frequencies that I need. What does this translate into? This is what we call bandwidth, right? And this is the range of frequencies that I need to build speech signal. How large is this range?
Depends.
We know that. 4 kilohertz, right? In the case of speech signal. How was this 4 kilohertz determined? Where is it coming from? Me doing this, right? I went and I said, okay, let me collect all of these things. Let me take their Fourier transform. And then I take first one, second one, third one. I put them all, let's say, on a transparencies on the top of each other. And then I do averaging. And I say, okay, well, it turns out nothing that anybody has ever said had any frequency content in this area, right? So this is how I determine the bandwidth of any random process. And that always travels with random process, right? We say, okay, this is a speech signal. The bandwidth, 4 kilohertz. This is music, bandwidth, 15 kilohertz. This is video, bandwidth, this much, right? So this is how it's determined. And not only that I know how far it extends, I know the relative contribution of each band, right? The speech signal wouldn't look like this. There will be nothing around DC, right? There will be some different shape here. But you will actually get what portion of the speech are contributing to what portion of the spectrum is significant for the signal, right? Where does the signal have its energy? Go ahead.
Does it always come with the time domain signal? If I have
What is it? Does it always
the
come?
signals, I mean, like you have the from time domain, like you slightly change into the Fourier
Well,
transform.
we live in a time domain, right?
Right,
So most
right,
of
but-
our signals are functions of time. I mean, this whole process is kind of basic, right? You can abstract this and define this, make this T space, for example.
Yeah, like you
And a
record
lot of
something,
times we do talk about spatial correlation, and then we talk about spatial bandwidth and stuff like that. When you process images, we do the same thing over there too, right? To define the frequency content of the image. But then over there,
and you come with fast Fourier transform.
the independent variable is not T, it's space, right? So
Right,
you can talk
space.
about the image as it is changes spatially, right? And there is a completely equivalent way of defining things. But in our course here, it's always, you start with time domain, but time domain, although we live in a time domain, is not very analytically comfortable for us, right? So we always like to eye what's happening in the frequency domain. A lot of times the picture is much clearer over there. What I want you to understand here is the physical meaning of the power spectral density. If I give you power spectral density associated with the random process, what information you can get from that is actually two significant pieces of information. One is, how broad is this signal in a frequency domain? What are the frequencies that I need to use to build this signal, right? And from there, the most important information you need is the band, right? When am I going to cut and in terms of frequency and not even notice that in a time domain, right? So that's the first. And the second one is, what portion of the spectrum is important in a signal, right? Where is the largest energy of the signal? And I want to make sure that if I'm designing communication system, first, that it allows this bandwidth to go through, right? And the second, that the portions of the signal where it has significant energy are treated with respect, right? That's the portions of the signal that needs to be treated, you know, and preserved as it goes through the system. If there is a portion of the spectral axis where the signal has no energy, I'm actually get rid of it, right? And I will not notice that in the signal. That's the information that I get from the power spectral density. Now, what I don't like about this whole thing is how messy this is, right? How complicated is this process? And this is where we kind of luck out again. There are all of these, you know, seemingly accidental things where we kind of just luck out, right? And here's the one of the fundamental theorems that help us here tremendously.
Excuse me, Professor.
Go ahead.
Please correct me if I'm wrong. I mean, like, in this case, we just, we need to understand what power spectral density is too. I mean, like, we're looking for energy of the signals and determine the bandwidth. That's all. Am I
No.
correct?
Yeah, but for right now, we're defining it, right? And what it tells us is what portion of the frequency axis is significant for this signal. You know, what are the sinusoidals that I need to use to build this signal, right? And it's in practical terms, we need a range, and we need their relative importance, right? Relative importance, because if they're not important, maybe I just get rid of them, right?
Right.
And maybe like if this kind of tapers off like this, maybe this stuff is so small in energy that I can just say, okay, this is what is important for my signal, right? So where is the saving?
So in this case, is the noise included in this spectral
No,
density?
in this case we're just
Just
looking at signal.
speech, okay.
We're going to look at noise the same way. This is just a random process: speech, noise, music, video.
But they all combined, right?
Correct. And we'll come to that, right? But right now we're treating them individually. Now here's our theory. And I don't know if you guys go to circus and stuff, but there's always a main act where there's music and then everything stops, right? Because there's nothing more dramatic than silence. Well, I cannot recreate that event now, but this is where it should happen, right? So this is the main act in this circus here, right? And this is a relationship that says this: if x of t is stationary and ergodic, and let Rx of Rx of t be this limit when t goes to infinity, 1 over t integral over t x of t minus tau d tau. In other words, let this be autocorrelation function. Then Fourier transform of the autocorrelation function is the power spectral density. Right? So, where I would say where Sx of f is power spectral density of x of t. Okay? So, this is what we care about. What we didn't like is how you get to it. We define autocorrelation function, and you saw that autocorrelation function is very easy to calculate.
So how exactly?
dt.
Where?
Inside the
dt.
integral,
It should be dt.
or it has to
dt,
be
dt,
yeah.
dt. Sorry. Now, autocorrelation function and the convolution, they are just by one letter difference, right? So always pay attention to what I'm saying and what I'm writing, right? Because they are not always the same. And they should. But here's the big thing, autocorrelation function we can determine relatively easy. We didn't know its physical interpretation up to now. Now we are able to say, why do we need autocorrelation function? Because if I know autocorrelation function, I get the power spectral density. They're Fourier transform pairs. They're the same, two sides of the same coin, right? They tell us the same thing, the behavior of the signal in the time domain. So, if instead of doing all of this, what I can do is, especially if the signal is ergodic, and then I can actually take 6 o'clock news only. I don't have to aggregate all of these different speeches and samples of the realizations of the speech signal, and I can run this through autocorrelation processing. And as a matter of fact, just take the signal, delay it, multiply it, and average over time, and then I delay it a little bit more, average over time, delay, and I get my autocorrelation function. If I take the Fourier transform of that, I get the power spectral density. So that's where the importance of it. The proof of this is very long. I don't know if I know it. I saw it once. So huh?
But the goal is really simple.
But the idea is very simple, right? The idea, and it shouldn't come to surprise to you, right? Because they're both kind of after the same thing. Let me go through an example, and then you can see how intuitively both autocorrelation function and power spectral density tell you exactly the same thing about the signal or the process. So let me go through an example here. So, example. Consider a random process that has autocorrelation function Rx of tau is equal to e to the minus tau over some capital T. So that's an autocorrelation function for every T, or every tau, sorry. Now it says determine power spectral density, and then we'll look at what happens when you change the value of capital T. So the power spectral density associated with all the process Sx of f is, according to Wiener-Khinchin theorem, it's the Fourier transform of your autocorrelation function, which is integral when tau goes from minus infinity to plus infinity, Rx x of tau e to the minus j 2 pi f tau d tau. This is what I need to crunch here And now the linear systems students are going to feel here at home. So let's put that in here. So this becomes e to the minus tau over t, e to the minus j 2 pi f tau v tau. And let me see how I do this here. Okay, I don't know if this is the simplest way, but I realize that this part is even, this part has an even and odd part, so I'm just gonna, or maybe not, but actually just one. So the odd part is gonna go away, right? So I just need an even part from here and even part from here. Now odd part is also imaginary part too. Do you see that? So the imaginary part goes away. Okay, let me slow down. Let me just write this one more time. So this is integral when tau goes from minus infinity to plus infinity, e to the let's say minus tau over capital T, and then I have cosine 2 pi f tau minus j sine of 2 pi f tau d tau. Okay? Right. Now you can see that the first part survives. The second part goes away. But the second part, if the second part goes away, that means everything that multiplies j goes away. Right? Right?
Yes.
Yes. So now, knowing this, I can say that this here is equal to the real part of, and I can say 2 times real part of tau goes from 0 to plus infinity, e to the tau over capital T with the minus here, e to the minus j 2 pi f tau d tau. Right? I need to take the real part. Okay? And then whatever is imaginary, that's going to go away. And then because the real part is even too, I can integrate only from tau to infinity. Now this integral is quite easy, right? It's just e to the something. So that's why I'm going to copy it from the. I'm just kidding. So it's 2 times the real part. And then you see this is e to the sum of these two, so it's e to the same thing divided by whatever is upstairs. So it's going to be e to the minus tau, common for these two, 1 over capital T plus j 2 pi f, and then divided downstairs by 1 over t plus j 2 pi f. And since I forgot this minus, I'm going to flip the boundary, so it's going to be 0 to plus infinity. And then when you substitute 0 upstairs for tau, you get 1. When you substitute infinity, you get 0. So it's just 1 upstairs. So this is 2 times real part of 1 over t plus j 2 pi f. And then if I multiply top and bottom by its complex conjugate, you get, let me do this, it's 2 times the real part of t over 1 plus j 2 pi f t. And then this is 2 times real part of 1 minus j 2 pi f capital T over 1 plus 2 pi f t quantity squared, multiplying top and bottom by complex conjugate. And if you multiply bottom by complex conjugate, you get the magnitude squared, right? This is 1 plus j 2 pi ft times 1 minus j 2 pi ft. Right? So this is 1 plus 2 pi ft quantity squared. And let me just finish. And then you take the real part, this separates, so this is real, this is imaginary, so the answer is 2 over 1 plus 2 pi ft quantity squared. Go ahead.
If you finish until that, the first one,
Uh-huh.
it's good or not? I mean, like,
This one,
yeah, until that one, not multiplied by t or the.
I multiply top and bottom by t here, right?
Right, right,
So I get rid of 1 over t, and there's a t here, and there's t upstairs.
right, right.
And then I want to get rid of complex number
Yeah,
downstairs.
you multiply
So I
by-
multiply by the complex conjugate
Right,
of whatever is downstairs. I get complex conjugate upstairs and the magnitude squared downstairs.
But
And then-
Is that minus there?
yeah,
This minus,
No, no, down.
down, the,
No, because-
Yeah.
where is?
J squared minus 1.
one,
Oh, okay, let's review that. X plus jy times x minus jy. This is x squared plus jyx minus jxy and minus j squared y squared. What is j squared? Minus 1, so it's x squared plus y squared. Right? So the number times its complex conjugate is the real part squared, if you want to be real part squared plus imaginary part squared. There's a plus here.
Yeah, we still lose t.
Say again?
T is lost there.
The answer is 2 into t.
no,
No, the t will multiply everything there. So is that you're right?
There's a t outside.
Yeah.
right.
Okay, sorry, yeah. You're right. Okay, t is missing. All right, so that's math. Let's just discuss the physics. Let's plot what happens. Consider, let me just leave this stuff upstairs. Consider two cases. T equal 1 and t equal 10. Here's t equal 1. What does autocorrelation function look like? If you look at the expression here, for t equal 1, this is e to the, and tau equal to 1, this is 1 over e. So it falls off to 1 over e of its value when tau is equal to 1, right? So if I plot this as a tau, and let's make this 10, let's make this 5, let's make this 1. It goes from its maximum like this, right? That's my autocorrelation function. So the autocorrelation function drops off very rapidly. What does that mean physically? Remember what the correlation says. You delay signal and you take the dot product signal in itself. So what this says, for a relatively small delay, the signal decorrelates. What kind of signal are we talking about? Something fast, right? Because I change it, I delay it a little bit, and all of a sudden it looks different. It changed, right? So this is a fast signal. The signal that behaves this way is let me do this. Kind of plot the time domain. So this would be x of t. It will be like this. The signal is changing very fast. Therefore, its autocorrelation function is narrow, right? Now, let's look at what does the power spectral density of this look like. So if I put f here, and I now plot Sx of f, let's see where the t is here. Now, for t here small, right? You see that this part of your denominator is actually going to make this equal to 0 eventually. But because t is small, it will take a large f before this starts decreasing, right? You see that? for this product to be significant, because capital T is small, f needs to be large. So if I were to plot this Sx of f, this is how it might look like. Right? It will be wide open, right? It will take quite a bit of f before it starts decreasing. Let's take a look at now, so this is for t equal to 1. Let's take a look what happens for t equal to 10. Now, this is 10 tau, where the signal was at 1 before, which is 1 over e at this point. It is now reaching that point when tau is equal to 10. So now your autocorrelation function looks like this. Right? It's slowly changing. It's wide open. How does the signal look like in a time domain? Well, here's my other guy. Remember the other guy. It is changing slow. Why? Because for small delays, this signal looks like itself. It hasn't changed much, right? So that's why its autocorrelation is large for small delays. I need to delay it by 10 before it decorrelates, right? So what do I know about this signal? It is changing slowly in time. That's why its autocorrelation function rolls off slowly. Now let's go back to our power spectral density. Here, T is large. So F can be small before this becomes significant. So if you look at the power spectral density associated with this signal, it looks like this. Okay? So do you see now how both of these capture exactly what we were set to do at the very beginning, right? We said, well, how do I capture this behavior? How fast the signal is changing along the t-axis? And I can do it either way. I can look at autocorrelation function, which is easier to compute, just in a practical scenario. This is relatively easy to determine. But once I know it, I actually know its behavior. And what this tells me is the behavior of this, what are the sinusoidals that I need to build this signal? And this is intuitively should be very kind of, I should say, familiar to you. This signal is fast. Therefore, to build these signals, I need sinusoidals of a high frequency. If I'm building something that is changing fast, I need fast building blocks, right? I cannot build fast changing signals by using DC components. How am I going to do that? The signal, I cannot do it. I need high frequencies. Here, the signal is changing slowly, so I don't need high frequencies. I need a lower frequencies. It's always good to look at two extreme cases. What's on this end? Extreme case here. Imagine the signal that is the slowest signal of them all. Which is the slowest signal? DC signal. How does the autocorrelation function of DC signal look like? It's a line, right? You shift it, it's the same thing. You shift it again, same thing. So its shifted version is perfectly correlated to the signal itself. So the autocorrelation function is always the same. It's always the power of the signal, right? Because no matter how much you shift it, you're taking the signal itself, and then you're multiplying, averaging, so you're taking the power. So autocorrelation function of a DC signal is a straight line. What does the power spectral density look like? It's just a pulse at the DC, right? So I need only one sinusoidal to build this guy. Which sinusoidal? With the frequency f equal to 0, right? DC component, right? So that's on one side. What is the signal? Let's take a look at this extreme case. Imagine the signal for which the Sx of f never rolls down. The Sx of f is constant, right? It goes forever. That's the signal for which I need all sinusoidals. Which signal I'm talking about? White noise, right? There is the signal for which we theoretically imagine consists of all sinusoids, right, has a constant power spectral density. We call that signal white noise because it has all the sinusoidals and they're all the same magnitude. Well, how does the autocorrelation function of that signal look like? It's an impulse. So that means that signal is infinitely fast. As soon as I move it a little bit, it looks completely different, right? It completely decorrelates. And that's a sign of an infinite bandwidth. It changes as fast as it can change, right? So these are the two extremes. So on one extreme you have DC, on the other extreme you have infinite bandwidth white noise, right? And all the other signals are in between. And then we can characterize their behavior by either specifying the autocorrelation function or specifying their power spectral density. All the autocorrelation function is, as I said, easier to compute. In practical world, we always kind of specify this. That's why that relationship that I gave you that has two convolutions is not the one that we use most of the time. The one that we use is the following. So let me go through that real quick. So transmission of random process through linear system. Here's what we have. We have, and this is the same drawing as we started with. We have x of t, but now as a process, and then y of t. And then there's this guy which has x of t, and its Fourier transform, which we call frequency response, which is x of f. We have the following relationship, which I kind of explained to you how you would get that one, that ry y of tau is going to be rx x of tau convolved with h of tau convolved with h of minus tau. Let's take the Fourier transform of this. What's the Fourier transform of autocorrelation function of y signal? Fourier transform. So Fourier transform of the left-hand side is Sx of f. Now Fourier transform of autocorrelation function for x is, should correct me here, right? S violet, right? And then what's the Fourier transform of this? Sx of f. What's the under quotes Fourier transform of convolution? Multiplication, right? What's the Fourier transform of the impulse response?
H of f.
H of f. Now the tricky part. What's the Fourier transform of this? Complex conjugate. There you go. Linear system, right? So complex conjugate. And then you end up with a good old friend. Power spectral density of the output is whatever is the power spectral density of the input times the magnitude squared of the amplitude response of your linear filter. This tells us exactly how does the linear system change power spectral density of your random process, right? And that's one of the most fundamental formulas that we're going to be using throughout this course. All right. So let me assign homework. I have forgot my notes. So there are a few more problems here, right? But I forgot the notes, so I have just two. You gotta remind me next time to give you more.
I have a question. Based on your notes on your website, homework is kind of like slightly different. I don't know. Have you updated?
Yeah. Use the one that I assigned in class because I'm adding some more problems. Right. So there will be two or three more problems here. So go by what I assigned in class.
Are you going to have some terms like in the linear? Like tan with of the both,
Yes. That's